I'm Ben. I'm an Android developer relations engineer at Google. And today we're going to be talking about Jetpack Compose debugging. We'll start by going over the mindset you should have when trying to debug a problem. Once we have a framework set up, we'll jump into some common issues we've seen people face when debugging Compose. When debugging, it pays to have a set process you go through. This generally follows the pattern of define, reproduce, test, and fix. First, we want to define what the problem actually is. What do you expect to happen? What is happening instead? Why do you think that should happen? And what assumptions are you and the code making? It always pays to have a reproducible example. That way, you can test out your assumptions and see which one of them is wrong. It also pays to write a test. This allows you to verify the fix and, as a bonus, could stop regressions in the future. That is, to stop it from happening again. You should then start by testing your assumptions. You can use the tools to assist you. Different tools will suit different problems, and we'll cover a full range of tools in this talk. Once you've worked out which of your assumptions was wrong, you can implement the fix. Run your test to verify the results, and to make sure you didn't break anything else in the process. Now we've set the groundwork for how to go about debugging, let's go over some common questions we have seen. First, probably the most common question we hear. Why is this composable recomposing? Let's define our problem. Our composable is recomposing, and we don't know what argument has changed to cause it. For our assumptions we are making, there are different types of recomposition. Direct recomposition, indirect recomposition, and also unskippable recomposition. Let's see some examples. This is an example of direct recomposition. We have some compose state, a count. When the compose state is changed, wherever we read the state, in this case, in the arguments being passed into this text composable, compose will automatically recompose. This is a direct recomposition. An indirect recomposition occurs when a composable is not directly reading a state object, but its arguments change regardless, due to some other calculation occurring. In this case, we are simply doubling the count. Count is the compose state object. And so when we read it, when calculating the doubled value, that is what causes the recomposition. But the arguments to my text have also changed, and as such, it is also recomposed. The third example is probably the trickiest to understand. Here we have the same direct recomposition as before, with a count and text updating when the count changes. This time we have an additional list composable that takes a list of numbers. When this composable recomposes, because of count changing, you might expect the myList composable to not recompose, as its inputs have not changed. But this is not currently the case. List is an unstable type, because we cannot guarantee its immutability, and as such, myList is recomposed also when its parent recomposes. This can all be a bit hard to comprehend, especially in a complex codebase, and that's why I am excited to share a new feature in Android Studio Hedgehog, recomposition state in the debugger. Now, when setting a breakpoint inside of a composable, when the breakpoint is hit, the debugger will show you the composition state of that composable and help you diagnose recomposition issues. The debugger will show the changed state of each of the arguments being passed into a composable. The states are as follows. Unchanged. Pretty self-explanatory, this argument did not change. Changed. This argument has a different value than the last composition. Uncertain. Compose is still evaluating whether this argument has changed. Static. Compose has determined this argument will never change. Unstable. This argument is an unstable type. Let's see a quick demo of the debugger in action. So now when I set a breakpoint and cause a recomposition by subscribing to a podcast, we can see the reason this composable is recomposed is because is followed is different. We can also see is followed is true. The debugger will also show us if we have an unstable argument, which we can see if we add a breakpoint here. Clicking continue, we can see that podcast is unstable. To sum up, recomposition state is now shown in the debugger in Android Studio Hedgehog. It allows you to see what arguments are changing to cause a recomposition. You can also step up a stack trace like normal with the debugger to find the root of composition and how the arguments are changing at each point of the call stack. This is just the start of our work with composition state in the debugger, and we will have more to share soon. But sometimes you might have something that recomposes frequently. Maybe a composable that is involved with scrolling or an animation, and you need to track the state over time. The debugger here would be annoying to use, as it would break too often and stop the flow of composition. In this case, logs are a great tool. There is nothing wrong with using logs to help debug. A quick example. Here we have a composable that is using the scroll state of a lazy list. In order to debug this recomposition, a log has been added to print out the current state. Now, after reading the Compose performance guidance, we try to defer the read to limit the scope of recomposition. But we notice our log is still being called frequently, and our scrolling list composable is still recomposing. The answer here is that the log itself is causing the recomposition. Because the log string is reading compose state, when that state changes, compose will recompose. The solution here is to wrap the log in a side effect. You could also simply just not log the actual state value if that is easier. So, logs can be very useful for helping to debug frequent recomposition. Just watch out they are not causing the recomposition in the first place. Next up, how do I know what's wrong with my UI on different form factors? With large screens, phones and foldables, it's difficult to make sure your layout looks and feels amazing on every screen. Are your font sizes appropriate on small screens? Is your text stretched too far on a wide screen? Are you adhering to accessibility and material best practices? Well, sometimes the easiest way to debug is to avoid the bug in the first place, and that's where linting comes in. In Android Studio Hedgehog, Visual Lint now supports Compose previews. That means that as you're developing your layout, you can make sure to catch and fix potential issues and optimize with material and accessibility in mind. You can quickly see your layout across multiple screen sizes, and if any have a problem, Lint will give you a warning or an error, even if it just occurs on one screen size. In this example, Lint is highlighting that our medium tablet layout has accessibility errors with voiceover and text color ratios. Next up, why am I seeing jank? I have here the Jetcaster sample app, and we have seen reports from our performance monitoring that on scroll of the top pager, there could be some jank. As this is a production build, we know that it is already running in release mode with R8 enabled, and we have a baseline profile all set up. What else could it be? Let's start by listing out some of our assumptions. We assume that the animating color background is not causing other composables to recompose. We are also assuming that because the pager items themselves are not changing, just scrolling, the pager items should not be recomposing. Let's dive in and see if we can fix this problem. Okay, so I'm in the Jetcaster sample, and we can see that if I scroll the top podcast pager, the background color animates its change. So in order to dive into what might be happening here, why don't we first open up the layout inspector. The layout inspector will highlight any recomposition that happens. So if I swipe again, we can see that these pager items are recomposing on scroll. And it's happening quite a lot. Now, you definitely don't have to worry about every recomposition, but recomposition during scroll is generally a sign that things could be done better. If I double click on the horizontal pager line, that will take us straight to the code where it is used. I'll set a breakpoint, attach the debugger, close the layout inspector, and swipe the page one more time. Now, with composition state in the debugger, I can see that the items argument is unstable. And when an argument is unstable, that means the composable can never be skipped. So anytime followed podcast recomposes, our whole page is going to recompose as well. Let's see if we can improve that. But before we dive into fixing this problem, we should write a test first. This will ensure our performance has actually improved by changing the stability of the parameters. Luckily, I have one pre-written using macro benchmark. This benchmark will find our pager and then swipe it 3 times. And we'll use this as a good performance baseline. So I'll run the test, and we can copy the results down as our before. And once we finish with the fix, we will make sure we've actually improved performance. So now that it's finished, I'll copy the results and we'll compare them to the after results. So I've implemented the fix by switching from a standard list to a Kotlin experimental persistent list. These lists are fully immutable and will allow our composable to skip. Now, when we scroll the pager, we can see that the pager items no longer recompose. And in fact, the entire followed podcast composable is being skipped completely. Now we'll just run the test again to make sure we actually improve performance. So now we compare the before and after results of our benchmark to ensure that we actually did improve performance. We can see that our medium frame duration, which is P50, improved by 17%. Plus, we saw small improvements in the other percentiles as well. This would be a good justification to ship this fix. So the incorrect assumption was that the pager items were skipping recomposition. This ended up not being true and was the source of our issue. We skipped over showing the actual fix here because we don't have time, but you can see it on GitHub. If you are facing a similar issue with recomposition due to unstable arguments, check out the Stability Explained blog post. Also, a quick shout out to baseline profiles. We mentioned at the top that this app already implemented a baseline profile, but if yours hasn't, it can be one of the most effective performance improvements you can make. For more information, see the baseline profiles link. To sum up what we saw, we used the layout inspector to help narrow down the issue and give us an idea of where to start. We then wrote a macro benchmark performance test in order to get a solid before and after picture of our issue. This ensures we are actually fixing the jank and not just guessing at its cause. We used the debugger to inspect the inputs to our pager and determined that one argument was unstable and causing the pager items to not skip recomposition. But now imagine you have the same reports, but the layout inspector doesn't reveal any clues where to look. What do you do then? Where should you focus on optimizing? So our problem is we have reports from production tracking that we have a high count of frozen frames. Again, because this is a production build, we know that it is running in release mode with R8 enabled. And we are shipping a baseline profile. The layout inspector didn't reveal any obvious problems, so we aren't sure where to go next. A great tool in this case would be tracing. A trace shows you where in your code you are spending the most time. This is a powerful tool to work out what is taking up the most time in your code and contributing to you missing the frame deadline and causing frozen frames or jank. There are 2 types of traces. System traces have low overhead, which means they are good for getting a realistic measure of your app. The downside is that they can only show code that is marked for tracing. When that is not enough, there is method tracing. A method trace shows you every method being called while the trace is running. Because of this, it has high overhead and will most often cause your app to run extremely janky. This means it cannot be used for a realistic time measurement, but generally you can still judge the ratio of time spent in each method compared to other methods. Let's see an example. This is a system trace. As mentioned, it only shows code that is marked for tracing. That means that with Compose, you will only see a block to show you recomposition, but you won't actually see what is recomposing in that time. By contrast, this is a method trace. It shows you everything. A bit overwhelming for sure, but sometimes that is just what you need. But what if there was something in between? A trace that gave you the speed of system tracing with the relevant information from method tracing? Well, thankfully, there is. Android Studio now supports showing composable functions in a system trace. You will be able to see what composable functions were called while the trace was being taken, and all with the low overhead of system tracing. To enable it, you just need to add the runtime tracing dependency to your Gradle file. But how do you actually read these traces? What does all this mean? Here is a simplified version of a system trace showing recomposition. Each bar from the top down is the total time of the bars below it. The bars also correspond to the stack trace of the functions called. Compose calls recompose on your composition hierarchy. The first composable is the material theme. Inside the material theme, we have a composition local providing the theming information. From there, the home screen composable is called. The home screen composable is calling the My Image and My Button composables as part of its composition. But why is there a gap? Gaps in system traces are from untraced code being run. Remember that system traces only show code that is marked for tracing. The code being run is happening after My Image is called, but before My Button is called, and is taking up the amount of time the gap is sized. Let's have a look at a real example of this. Okay, now that we know how to read these system traces, let's learn how to take one and use it to solve an issue. So I'm back here in the Jetcaster sample app, and I'm going to open up the profiler, click on the CPU lane, click System Trace, and then click Record. Now I'll use my app, so I'll swipe the pager 2 times. We'll stop the trace. And that's it. Now we've taken a system trace. In order to make this a bit easier to see, I'm going to open it up in Perfetto. So I've opened up the trace in Perfetto, and the 2 busy sections we can see here are the 2 times I swiped the pager. And we can see all of the recomposition happening. You can navigate this trace using the W, A, S, and D keys. And if we zoom in, we can see that there's this large gap inside the home content composable that's taking up a lot of time. So you could switch to a method trace here, or it often pays just to have a look at the code first to see if you can notice anything suspicious. So why don't we do that? Jumping back to the code, I've opened up the home content composable, which we know from our trace was where most of our time was being spent. Now let's just scroll down and see if we can see anything suspicious. Oh, hello. This looks a bit suspicious, doesn't it? Let's open it up and have a look. And now, just to verify that this is indeed the thing taking up all of our time, we can wrap this in a trace tag. You can give it any name you want. That is what will show up in the trace. So let's take our trace again and see if this was indeed our culprit. Opening up the trace, we can see big object is indeed the item that was taking up all the time in this trace. So now we know what our problem is. We can go and fix it. If you did find yourself in this situation, you could remember the object to stop it from being recreated on every recomposition. It could also be things like sorting a large list in composition, or really just doing any work that could be done outside of the UI layer. But really, this example was just designed to show you that tracing helps you find the problem. It doesn't fix the problem for you. Use system traces to help narrow down where to start looking for where you can optimize your code. Remember, system traces can only show you traced code. You can add your own trace tags if you need to trace something else. For tracing composable functions, you can use composition tracing. For the full setup instructions, you can use this link. Or switch to a method trace, which will show you every method call your app makes during a trace. And that's it for today. To sum up, here are all the tools we used. Compose Debugger. See what arguments are changing in your composable that are causing recomposition. Layout Inspector. Inspect layout issues and see recomposition. Visual Linting. Automatically discover layout issues that happen across form factors and more. Composition Tracing. See composable functions in a system trace. Benchmarking. Quantify your performance optimizations. Thanks for watching.